Quotient rule, power rule, right? And we've learned how to apply those to polynomials, square roots. We've learned how to apply those to trig expressions, okay? This is the last rule for derivatives, okay? That's it. And then the rest is just the different kinds of functions you'll apply it to. Okay, so we're going to learn this rule. We're going to practice it. And then it's just applying it to different kinds of functions and things that even aren't functions. One of the lessons you're going to watch later this week is how do you take the derivative of something that fails the vertical line test? Okay, so is there a way? Yes, there's a way. And that's one of your lessons. Okay, and that'll take you 2 days to kind of go over that. But we'll start with chain rule today. A chain rule is directly related. It's the rule you need when you're differentiating something called a composite function. All right, now, a composite function is identified as any function that has parentheses or could have implied parentheses in it. Okay, so for example, a simple composite function is the sine of x, because what is typically around x? Parentheses. Okay? All right, the square root is a composite function because what's a different way to write the square root? With parentheses, okay? So anything that has, you understand the difference between explicit and implicit parentheses? Explicit, like the parentheses are written there. Implicit parentheses are, the parentheses are implied to be there, but we are mature enough in our math that we don't always, like when I write x, implied there is that it's x to the what power? 1. That's an implied power. Okay, when you write the square root of something, what's implied is that there's a little baby 2 right there, but we don't write it because we're mature in our math. Okay, but with chain rule, you got to address both the explicit parentheses and the implicit parentheses. Those are composite, all right? And it works both for prime, which is Newton's notation, and it works in Leibniz notation as well. All right, so here we go. If you have a composite function that has either implied or explicit parentheses, then you can take its derivative as long as it's differentiable. And differentiable means you can't have any corners or cusps or vertical tangents or any discontinuities in that. So it's all of those rules still apply. Okay, if there's a corner, then the chain rule doesn't apply. If there's a cusp, the chain rule does not apply. All right, here's how the derivative goes. You work on the outside and you work your way in. The outside equation is the f equation. So you take f and you figure out its prime first. But in the parentheses, you don't change anything. Okay, so outside first, leave the inside alone. Don't change what's inside those parentheses. Okay. Then by multiplication, you're going to link the next part of the derivative. So the next part is you address the next function, which is the g. And you'll figure out g prime. But there's still parentheses around u, and you leave that alone and you don't address the u. This stays as it is. And then you link the chain, or you use multiplication, and then you finally address the u prime. So at the beginning, there was f, g, and u. There were 3 different entities. So when you're looking at the result, you should have 3 different pieces with 1 prime in each of them. So the first piece has the f prime part, but you don't address the g and the u. And then the second one has the g prime part. And then the last one would have the u prime part. This is called the chain rule because links in the chain. It's like chain 1, and then we link chain 2, and then we link chain 3, depending on how many different parentheses there are, because you can have lots and lots of implied parentheses. Some people talk about it like the outside in. Okay, work on the outside, leave the inside alone, then work on the next piece, but leave that inside alone, and then just keep working until you've gone all the way through. Okay, so how would it go if you had f, g, h, and u? Anybody want to try it? What would you start with? You start with f prime. But inside that, you'd leave G, and then the parentheses H, and then the parentheses U, all untouched. Leave the inside alone. Okay, then you multiply. What's the next part? Then G prime. And inside of that, you won't touch what H and U are. And then the next part would be then the chain, the link in the chain that would deal with H prime. And you leave the U untouched. And then at the very end, you have U prime. So every piece would have 2 of those. So you've been doing this without even realizing you've been doing it. So for example, if we had y sine x, and there are implied parentheses around that. When you guys take the derivative of that, okay, you deal with the outside piece. And what is the outside? Cosine. Okay, and you leave what's on the inside by itself. And then you take the derivative of what is on the inside, and the derivative of x is 1. Okay, so this has been working for you all the time because all the problems I've picked for you or that have been designed in the book always have a derivative of 1 on the end. So you haven't needed the chain rule. Multiplying by 1 doesn't change anything. But if you have y equals sine 2x, okay, then the derivative is going to be the outside, but leave the inside alone, and then multiply by the derivative of the part on the inside, which would be multiplying by 2. So those are some of the basic introduction to how the chain rule works. Anything with parentheses, implied or explicit. So we're just going to work through a couple different examples, and then I'll give you time to work in class. Okay, so if we want to take the derivative, this has one set of implied parentheses. And so we start with the outside. All right, what is the derivative of the outside? All right, negative sign. But the inside stays unchanged as 3x to the 4th minus 2. But because there is a set of parentheses, I follow that with the derivative of what was in there. Okay, so 12x to the 3rd minus, and then the derivative of 2 is 0. And we typically would clean that up a little bit. Okay, the minus 0, we don't need so much. So I could just write it like this. And then you'd probably write your final answer this way. You'd put the minus in the front. You'd probably put your 12x cubed first, and then put your sign towards the end. Now it's not wrong. It's equivalent to leave it. I'm just saying typical order would be the polynomial part first, and then the trig part second. All right, the second part where we differentiate next, you have to view that with the lens of, oh, there are implied parentheses in the square root. So first, you need to think of that as 3x plus 1 with parentheses to the half. Then when you want to take the derivative of that, then you'll apply the rules. So what's on the outside of this is the half power. So what rule will be applying to the outside? The power rule. Okay? So the power rule says pull the power down to the front and subtract 1. So that will give me 1/2 in the front of 3x plus 1, and the new power on that is negative half. Okay, I don't touch the 3x plus 1 yet. Then I do chain rule. Then I tackle the 3x plus 1, and the derivative of 3x plus 1 is 3. Okay, and you wouldn't want to leave your answer that way either, especially with the negative exponent. So you'd identify the only thing in the numerator is the constant number 3. And then what would be in the denominator would be the 2, that's from the half coefficient, and then the square root of 3x plus 1. Or you could write parentheses x to the positive half would also be fine. Okay, that's fine if you want to write it like that to the positive half. Either of those are equivalent. Just don't use a negative exponent. Okay, how you feeling about this so far? Yeah, Ethan.
On like the first one, say it was like minus 2x.
Mm-hmm.
Would it be, so you would distribute like the negative sign?
Okay, good question. So he said, what if it was minus 2x? Okay, then your derivative would have a minus 2, and the thing that would be out front would also have a minus 2, and you just put that in parentheses. But don't do any distributing or anything. No, I wouldn't. You can if you want to, but I wouldn't. Yeah. Okay, I better erase that, or that's going to look confusing to somebody later. Oops. Okay. All right. Sometimes there are a couple sets of implied parentheses. Okay, so it's always, always, always good practice, especially when you're first learning the chain rule for the first time, is to write all of the parentheses, the implied and the explicit ones, so you make sure you've got everything covered. All right, does anybody want to take a stab at writing this with parentheses? Okay, Rose.
Parentheses, sign, parentheses. I'm debating about putting
Wait, this square.
another parentheses, x, parentheses, close parentheses, squared, close parentheses. And then another close parentheses to the 1/3.
Okay. She was extremely thorough about all of her implied parentheses. All right. There is one, the one that you put on the very inside around the x, just the x part. The derivative of that little piece is going to be 1 at the end. So you don't have to have it there, but it is still a good practice to do it that way. So we'll just leave it for practice. All right, so she's got all of her implied parentheses with the cube root and the squared power and the sign. All right, so when we take our derivative, our y prime, or we could write it dy dx, both of those are the same. We work on the outside in. So the outside is the power rule on the 1/3. So I pull the power to the front and I subtract 1. So that's going to give me 1/3 sitting in front of the sign of the quantity of x squared, and the new power on that would be negative 2/3. What's the next in the line of succession? The sign. Okay, now I deal with the sign, and the derivative of that is the cosine, and in that I leave that interior part alone. Okay, then what rule do I apply next? Power rule again. And so I move the 2 to the front and I decrease the power to 1. And then the last part would be the derivative of just the little x that's in there, which is 1, which isn't really going to contribute anything to my my overall problem. So now we want to clean it up and make it look a little nicer. We're going to have a numerator and denominator. What stays in the numerator is the cosine. What else stays in the numerator?
2x.
The 2x. What should I probably list first? The 2x. And then the cosine. And I can just write x squared. I don't have to keep all those extra parentheses in that this time. And then my denominator would be the 3.
Cube roots.
Yeah, you can write it with the cube root if you want. You don't have to. You can just write it to the 2/3 power. You don't, but you won't, if you can't, you may write it with the cube root if you like. Okay, but that looks a lot better visually to separate the numerator from the denominator than it did when it was just one long thing. Yeah.
Would it be okay, like the numerator, to just write the 2x and cosine x squared next to each other without the dot?
Oh, sure. Yes, so like this. 2x cos x squared.
Yeah.
Yep. Okay. All right, here's another one where there's an implied something, but we maybe need to see it with the lens of, okay, I need need to write this a little bit more explicitly. The implied part is where we place the square here. What does that really mean, that square? It means the entire thing is squared. And so it's going to be better for you to think of this as a cosecant and a 5x to the third minus 2, and that whole thing is inside of a square. It will be better for you to think that way, because then you'll be less, it would be easier to identify what quote unquote is the outside function. All right, because I have seen students identify cosecant just because it comes first. They're like, oh, I must do cosecant first. But really, you're not doing cosecant first. What you really want to do first instead is you want to apply the power rule first, because it's the square that's really on the outside of your function. All right, so my y prime, if I'm doing the power rule first, pull the 2 out to the front and then subtract. So I'll have 2 parentheses, cosecant parentheses, 5x cubed minus 2, and that drops that power down to 1. Then I want to take the derivative of cosecant, okay? Because it's a co-something, it's going to be negative, and it's negative what? It's negative cosecant cotangent, but both of those have the 5x cubed minus 2.
Ew.
And then finally, I'll tackle what was in those shared parentheses. And the derivative of 5x cubed? 15. Now, it's technically parentheses x squared, but then when we multiply by the x derivative, it's going to be 1. So as you get more mature in this, you don't have to do that times by 1 every time. All right, so there's no negative exponents, but we can clean this up. What should we lead with? A negative would be good. And then what's our coefficient? 30. Why is it 30? I got a 15 here and I got a 2 here. So this is all multiplication, so this is 30. Okay, then what? Oh, wait, you're forgetting the polynomial part.
Oh, x squared.
X squared, okay, negative 30x squared. All right, then,
Cosecant squared that.
okay, so there are 2 identical cosecants. There's one here, and in multiplication, we'll have cosecant of 5x cubed minus 2, and then it's your choice whether you want to put your square around the whole thing or whether you'd like to put your square where it usually goes. It's your choice. There is no, either way is fine. And then the cotangent of 5x cubed minus 2.
Why is it not negative cosecant squared?
I pulled the negative out to the very front at the very beginning.
Oh,
So I basically took all of the coefficients. I took the 2 and the negative and the 15 and grouped those all together in multiplication.
I looked at my schedule. My schedule for GCU already has pre-calc.
All right, how about this one?
Great question.
All right, how many embedded sets of parentheses? So let's unravel this.
Wait, where is the?
Okay,
Oh, wait.
all right,
Can we just try it first?
Yeah, can you let us do it
sure.
so that we can know?
That was
All right.
I'm confident.
Letting
Sure.
you do it.
That was like
Okay.
we want to try this? Good luck. I'm sure.
Okay, remember, this was not my suggestion.
No.
How about we stop and just check that you've written it correctly
Yes.
with parentheses first? How about we do that? All right. Does anybody want to have a chance to think about their parentheses and want to share? You already did one. Who else? Who's got it written as parentheses? Lauren, how about you?
I said cosine parentheses 1
I think you got your 1/4 in the wrong spot. Does the 1/4 impact the cosine?
No.
Okay, so,
So there's the outside, set of parentheses after the 1/4.
Yeah.
And between the after 1/4 and 1/4.
so after cosine, after cosine, there should be a double parentheses. Okay, there's the cosine and there's the parentheses that are already there. And then would come the implied parentheses, which would surround the 1 plus tan. And then 1/4, and then we'd have the final closed parentheses. Okay, so what is our first layer? The trig, right? We want to tackle, sometimes I even label like what I'm going to do. All right, if this is going to be number 1, what's going to be the second link in the chain? The 1/4. That'll be number 2, so that'll be first. This will be second. What'll be third? Well, the 1 plus tangent. That'll be third. And then fourth. Okay, so first, second, third, fourth. All right, so our dy dx would start with negative sign, and then everything inside would remain unchanged. All right, so everything else remained unchanged. Then the second thing I'm going to tackle is the 1/4. So I'll pull that 1/4, and I'll have 1 plus tan 3x. And the new power on that would be what?
Negative 3/4.
Negative 3/4.
Forgot it too.
Okay. Then the derivative of 1 plus tan. Okay, what's the derivative of 1? 0. And the derivative of tan, secant squared, and then still of 3x. And then, nope, derivative of 3x, 3.
Then you get that 1.
This is gross.
All right, so now when I simplify this, I'll have a numerator and a denominator. All right? All right, so what should lead my numerator?
3.
Anything else?
Wait,
A negative. Negative 3. Okay.
What about the 1? Oh,
The
that's never mind.
1/4 is gonna, yeah, so
Never mind.
my negative 3 goes first. And what comes next?
Sine and secant squared 3x.
Okay, I'm gonna put my secant squared 3x next because it has the higher power. And then my sine, and I'll probably put it back to what it was. Beauty is in the eye of the beholder. Okay, all right.
No beholders.
Then, what goes in the denominator?
Do you need that?
I do, I was just noticing that. Okay.
4.
A 4,
Then 1 plus tangent 3x. Or parentheses 3x. All to the.
To
or
the
that is to the
3/4, which I could write as the 4th root and put a cube in there. But.
No.
Okay, so these are just, there's not going to be any word problems in your assignment tonight. I mean, these are all like, you're just practicing the skill and practicing the skill and practicing the skill. All right, last thing. Okay, find a tangent line. Okay,
Points and slope.
okay, it just means point and slope. So my point will start with what value? 1. And then plug 1 in.
1 is 3.
1 9.
No, 3 squared is 9.
Oh wait, that's 127. Yeah, you're right.
127.
Okay, 127. Now, to do slope, I'm going to need the derivative. To do the derivative, I'm going to have to see this through the lens of parentheses and stuff.
This one's not that bad.
Okay?
Is this quadratic? That's not a quotient rule.
This is not quotient rule.
But why?
How else can we see this? See it with the lens of how you want to do.
Third.
Okay? This would be 2x plus 1 to the negative third. Now, would it be wrong to do quotient rule? No, it's just going to be a lot harder, and the algebra is going to be all this reducing and foiling and everything. You'll get the same answer in the long run, but much, much easier if you can think of this in terms of its power instead.
So how do you know, like, which one is the best to use?
Well, okay, if you've got a coefficient that's just a 1,
Uh-huh.
that's going to be, you're always going to want to make this as a negative power. All right? In fact, negative powers are probably always going to be better than quotient rule. Okay. All right, so let's take the derivative. So what's the outside part of this?
Negative 3.
-3. And then the inside remains unchanged
Minus to the negative 4.
to the negative 4. And then I multiply that by the chain rule of 2. And then I'm going to want to think of this, put it back.
It's 2 over negative 3.
Okay, now what is, no, the negative 3 is not over. Negative 6 is my numerator,
Over
Close to being
2x
plus 1 to the 4th. All right, then I plug 1 into that.
That's 3 to the 4th.
Wait,
Well,
27
what's
times
3 squared times 3 squared?
That's a
9
fantastic
times 9
question.
is
Oh,
81.
Yeah,
6
so
over
81.
What's 81 divided by 6?
Well, they both can be divided by 3.
Oh, so 2 over, log division. 3.c2.
27, back to 27 again.
But,
That's crazy.
oh yeah, because, yeah, okay.
Okay, all right, so we write our tangent line. And our tangent line will be y minus the fraction 1/27th, the slope of negative 2 over 27, x minus 1.